this theorem is very basic, but it can be very useful. It says that if the series sum of a to the n equals 1 to infinity is convergent, then the limit of a to the n when n goes to infinity equals 0. Okay, so you have to be careful. This is not saying that if the limit of the a to the n goes to 0, the series is convergent. Okay, you have to be careful with that. So let me give you first an example of what the theorem is not saying. Okay, so example. So the theorem, or let's say they call it like a warning, because this is a very common mistake in the exams. Okay, so that's what I want to start saying. What this theorem is not saying. So let's put it like warning. This is like a bad use of this theorem, warning. So the sum, and we will see next why this is divergent. So sum of 1 over n equals 1 to infinity is divergent. Okay? And the limit of n goes to infinity of 1 over n is equals to 0. Okay? So it's not saying that if the limit goes to 0, the series is convergent. Okay? Because if you read it, this is like logic. Okay? It's saying if the series is convergent, then the limit goes to 0. The limit of this a to n goes to 0. Okay? So this theorem makes sense because you think about it. Let's say the series is convergent. So a to n, so the a to n goes something like this. So let me put the a to n's like lines, right? So this is a1, this is a2, this is a3, and so on. So if the series is convergent, these little values has to really go to 0. Okay, if it's, let's say, if any a to the n is bigger than 1/3, okay, let's see what happens. In my series, in my points, if in my series, my points so what I'm saying is my a to the n, the a to the n has to go to 0. Okay, so these are the a to the n's. Okay, if they do something like this, if they stay here up, you see, they stay here. Let's say this is 1/3. If a to the n is bigger than 1/3, well, so a1 is bigger than 1/3, a2 is bigger than 1/3, a3 is bigger than 1/3. So a1 plus a2 plus a3 would be bigger or equal than 1. Okay, so since you have infinite sum, eventually this sum, it has to be infinity. You are gonna keep adding once to the series, so the series has to be divergent. But if it's convergent, if your series is convergent, then this guy has to, those points has to go to 0. These points, A sub n's, the A sub n's, at some point needs to start going down. Okay, so let's see what is the best use of this theorem. So the best use of this theorem is the test of divergence. It's kind of the real logic. So the logic behind this, we have P implies Q, right? This is equivalent to no Q implies no P. Okay, so politicians, I'm talking about elections, right? Politicians all the time lie because they use the logic wrong. Okay, all the time. Even there was a famous case of the Simpson case. I remember even there is a series about that. The argument of the lawyer that gave him freedom, it was illogical. At the end, it was not a true statement. So it was a run of statements, and at the end, it was wrong. So it was a famous mathematical logic argument or puzzle. And so let me give you the test for divergence. That is the negation of the statement that I give you at the beginning. Test of divergence. So it says if limit of A sub n when n goes to infinity is different of 0 or does not exist, then the series is divergent. The series is divergent. So this one is important because I think that's probably the I'm gonna ask you, I'm gonna give you a lot of series. And I'm gonna give you a lot of series. So I think when I say series, I think my iPhone is thinking I'm saying Siri, and then she's waking up. Sorry. Let me turn my cell phone off. I'm gonna give you a lot of series, so you need to decide if they are convergent or divergent. This is the first test that you probably should do. To see if it's divergent, you don't waste time. So let me give you some examples. But basically, this test of divergence tells you what is bad. Okay, it's gonna tell you right away when a series is bad. So let me give you something easy. So let's say trivial. Okay, sum of n equals 1 to infinity. Let's say phi n. Okay, this is a series. What is the limit of phi n when n goes to infinity? What do you guys say? What's the limit of phi n when n goes to infinity?
Infinity.
Infinity. So is the limit of the sequence is the divergent. Therefore, this series is divergent by the divergence test. But of course, this example is too easy because I know that 5 plus 10, I know that 5 plus 10 plus 15 plus 20 plus 25 and so on. Well, that's by sure is going to go to infinity, right? So here the divergence test is not very useful. Okay, but let me give you another one. So, well, let me remind you this one. Okay, here 1 over n, let's say I give you sum of 1 over n. So you go and say the limit is 0 and said, oh, then it's convergent. No, this is going to be divergent. So it only works for bad, okay? It doesn't count anything good of the divergent test, okay? In this case, if the limit goes to 0, then you cannot decide. You cannot apply the divergent test. So let me put it here. You cannot apply divergence test, okay? Because it's just, it doesn't apply, okay? The divergence test is saying if the limit is not 0 or does not exist, then the series is divergent. So let me give you one that is not that easy. Yeah, let me give you this one. I'll give you 2 minutes to do this one. So show that the series sum n equals 1 to infinity n squared divided by 5 n squared plus 4 is divergent. Okay, so this is divergent. I'm telling you that is divergent. So you need to show me that is divergent. Okay, so go ahead. So let me give you 4 minutes to do this. Okay, let's do it. So remember, these are critical examples since we are not meeting, but I usually in class, I will give this problem and whoever finish, first 5 or 10 people that finish, I will give them like quiz grade. I cannot do this because it's too complicated, but I try to keep you engaged, because this is important, okay? Because these are critical problems that people got wrong very easily, okay? Okay, so I need to show this divergent. So my first chart should be using the divergent test. The divergent test says that if this limit of the sequence n squared phi n squared plus 4 is not 0, then the whole series is going to be divergent. So I need to show, and you need to, when in the exam, you're going to have to show me and tell me why is this not divergent. Not just say it's divergent or not, because you can put it in your calculator. You need to show me, otherwise 0 credit. So what is this limit? So let me say, let's use the divergent test. So we need to check this limit. So what is this limit? How do we find that limit? You guys remember? What is this limit? Somebody found it? I'm sure somebody knows. For pre-calculus or some reason, you know this limit. What is this limit?
0?
No.
Ah, shit. Oh, it's 1, isn't it?
No.
Ah.
Is it 1 over 10?
1 over 10? No.
1 over infinity?
No.
Huh.
What about ladies?
1 over 5?
1 over 5 is correct. Yeah. So how do you do it? So remember I did this before, but in pre-calculus, you do these limits, and in calculus too. You have n squared and n squared. When the power is the same, the limit is just what is next to the higher power. In this case, 1/5. But let me do it. So we have limit n infinity. So what I did, remember, is that I divide by the biggest n squared, in the bigger power of n. So in this case, it's n squared phi n squared divided by n squared plus 4 divided by n squared. Okay. And then we cancel. That's 1. This cancel. That's 1. So I'm getting that this limit is similar. I haven't found the limit yet. I'm just doing like algebra trick. I get 1 over 5 plus 4 over n squared. Now what? Now I can do split the limit in a quotient. Okay, so I can find the limit of the top over the limit of the bottom. The limit of 1 n goes to infinity divided by limit n goes to infinity of 5 plus 4 n squared. So what is the limit of the top? What is the limit of 1 when n goes to infinity?
1.
1. And what is the limit of the bottom?
5.
5.
Because this guy goes to 0. So I get 5. So this limit is not 0. So since well, let me write it down here, because you're gonna have to get an argument. Since the limit of n squared over 5n squared plus 4 when n goes to infinity equals 5 different at 0, by divergent test, by the divergence test, the sum of this guy, n equals 1 to infinity, n squared divided by 5, n squared plus 4, is divergent. Okay? So that's a good example of what you can use with that theorem. So to move to the next section, let me remind you some properties of series. Properties of series. Because you can split your series. Okay. So the first one, first property, if you have the sum of a constant times a to the n, you can just take the constant out and find the sum. Okay. Well, let's say property of series, if they are convergent, right? If they are convergent. If they are convergent, let me say, so what does it mean convergent? That means if simply means that the sum of a to the n is less than infinity and the sum of b to the n is less than infinity. That is convergent. Okay. So if the sums are convergent, or what it means is the sum gives me a number. So all these properties follows. The second one, you can add or subtract two series. So you can get sum of n equals 1 to infinity, and then you can get a to the n plus minus b to the n, and then that will be the sum of the first one plus minus the sum of the second one, if they are convergent. Okay. So I'll give you more examples next when we have more examples of convergent series. So far we only know that the geometric series is convergent. So, but this is what is next. The next is very important one. This is probably our best tool, the integral test. Okay. Let me put it in red. The integral test. So the classical example of an integral test is the following, because it breaks your intuition. So you take the function f of x equals 1 over x, and it's something like this, right? And then you take the function g of x equals 1 over x squared, and that one decreases faster than the other one. So we know that we can make sequences here, right? So you can see sequence. This is another important thing here. How can you see a sequence? You can also see a sequence as rectangles. Okay, you can make, let me make it blue rectangles. So this is 1, this is 2, this is 3, this is 4, this is 5. Or better that you can see it like a left Riemann sum. Okay, like a left Riemann sum. You can see a sequence. You can visualize a sequence as a left Riemann sum, because you know A1 is this guy, and you see this is the high, And this is the base. This distance is 1, right? So this guy here is A1 because it's f of 1, right? A1 is f of 1. 2, if you have 2, I will get f of 2. This is basically my area here. My area here is just f of 1. My area here is f of 2. My area here is f of 3. My area here is f of 4. And so on. Okay? That will be my series. Okay? Over here, do the same. I do the same thing. 1, 2, 3, 4, 5, 6, and so on. So here I'll get my left-hand sum. Will be this one. So the rectangles are smaller. This is G of 1, G of 2, G of 3, G of 4, and so on. But remember, f of 1 in my notation is A1. This is FA2. This is A3. This is A4. Okay, so you see this left Riemann sum, how useful has been for us. And this is, let's call it B1. This is B2. This is B3. This is B4, and so on. So it turns out that the first one, 1 over x, this series is going to be divergent. The green series is going to be divergent. The red series is going to be convergent. So example. And then we are going to prove it with the test. Example, very important example. Sum of 1 over n, n1 to infinity is divergent. And B, the sum of n equals 1 to infinity, 1 over n squared is convergent. Okay? So how are we going to prove this? So we have to spend all this time find integral, so it must be good for something, right? So we're going to use it. Because you can see there is a direct relationship between the sum and the area of the curve. Okay. We could also use, instead of left, use right Riemann sum, or right-hand Riemann sum, right? Like I call it. And you'll see that the rectangles are below of the integral. Okay. In that sense, you see that if the area, if the integral of the function is less than infinity, then the series must be convergent. Okay. So yeah, so probably the book does it with the left-right sum, but we could do it with the right-hand sum. And then it will be clearer that it's convergent. And so this is the integral test. So this could be the most important one that we're going to do. The integral test. But it's not that easy, okay? The integral test, you need 3 requirements. So you need to prove. So assume f satisfies the following. So before using this powerful tool, an easy tool, you need to prove first, 1, f is continuous. 2, f is positive. 3, and the hardest, f is decreasing. Okay. So is the decreasing function. All this on 1 and infinity. So f is a continuous function on 1 and infinity. All this is in on 1 from 1 to infinity. On 1 to infinity. 1 to infinity and on 1 to infinity. Okay. If f is this nice, and we let a sub n equals f of n, then the series sum of n equals 1 to infinity a sub n is convergent if and only if the integral is convergent. And in other words, so let's say this is, and this looks like a lot of conditions, but this thing might be confusing for you. So let me put it clearer. What is if and only if? So that means the following, or in other words, if the integral from 1 to infinity of f of x dx is convergent, then the sum is convergent. And 2, if the integral is divergent, remember divergent means that is infinity, okay? Then the sum is divergent. Okay, so using this, so we're gonna do 2 examples. And please make yourself a favor and do these examples, okay? This is fundamental. So example 1. Show that the sum from from n equals 1 to infinity is divergent using the integral test. You know, when I was showing you the notes, I skipped some things because in the notes they show that this sum is divergent in a long way. So I don't want to do that because I have the integral test. I don't want to confuse you. So let's do that with the integral test. So let me help you a little bit. You want to show that this series is divergent, right? Using the integral test. So what is f of x?
1 over x. What? 1 over n.
1 over x. That's correct.
Okay.
So now what do you have to do?
The integral.
Right. Integral, but before the integral. Because otherwise you're going to lose half of the points in the exam.
Okay.
Huh?
check for the rules.
Yes. Let f of x and check 1, 2, 3 conditions. So you need to check f is continuous. That's easy, right? F of x is continuous between 1 and infinity. Yes, that's good. F is positive. In 1 and infinity, yes, it's positive. Now f is decreasing. So you show me that f is decreasing. Otherwise, you cannot use the theorem. Okay? I mean, you can use it, but I will take points off. If you don't show the function is decreasing, I will take 2 or 3 points off. Probably 3 points off. Because you need to show that the function is decreasing. Otherwise, you don't use the integral test. So show that the function is decreasing. So you need to show the function is decreasing and find the integral. Well, okay, so at least find the integral. So go ahead. So let me give you 4 minutes to do this. Okay, let's do it then. So first we need to check. So we need to check 1, f of x equals 1 over x is continuous on 1 to infinity, right? This is fine. This is just like this, right? Why is this function not continuous? 1 over x. The function is not continuous at 0 because I cannot divide by 0. Okay. So the other thing was f is positive. So 2f is positive, yes. In 1 infinity, f of x equals 1 over x is bigger than 0 on 1 to infinity. You just need to see the graph, right? So it's on the top, in the first quadrant. So it's good. The third one, sorry, is that the function is decreasing. How can I show that the function is decreasing? I mean, you can graph it, right? You can show the function is decreasing. That's probably okay. You just show me the graph that the function is decreasing. It's okay. But in one other way you can check that the function is decreasing. What did you learn in calculus?
On the limit.
No, because this is decreasing and increasing. How do you find that function is decreasing?
The rate of change.
Mm-hmm. Okay, that's the rate, but that's in pre-calculus. How do you call the rate in calculus?
The derivative? No.
Derivative, yes, sir.
Oh,
derivative. So the derivative is the rate of change. If the derivative is positive, the function is? What is?
Decreasing.
Increasing, thank you. If the derivative is negative, the function is?
Decreasing.
Decreasing, yes. So this is 1 over x is just x to the minus 1, right? When I find the derivative, I get minus x to the minus 2. So I get minus 1 over x squared, right? So what do you think? This function is always negative. The derivative is always less than 0. In particular for on 1 to infinity. Therefore, f is decreasing. That's the only price that you had to pay. Well, that and find the integral. So then it looks like I can apply the test. Now, in practical conditions, you check the decreasing at the end. Because if the integral is not going to be, you cannot find the integral, why do you waste time, right? So in practical conditions, you do the increasing, decreasing at the end. But we need to find, so let's use the integral test. My pen is really breaking apart. Sorry, my writing looks even worse. So we use the integral test. We need to find the integral between 1 and infinity of f of x, that is 1 over x dx. So we already did this, right? So this is the limit of a goes to infinity, u1, integral from 1 to a, 1 over x dx. And then this is the limit of a goes to infinity. And then what is the antiderivative of 1 over x?
ln absolute value of x.
Thank you. Between 1 and a. So when I plug in a, plug in 1, so I just get limit of a goes to infinity of ln of absolute value of a. And what is this?
the absolute value. No, ln absolute value of infinity.
And what is that?
0.
No, because ln goes this way. right? So when a goes to infinity, where is the function going?
Infinity.
X, okay? The function is going to infinity because it's ln of a, and a is going increasing, right? So that's infinity. So by the integral test, you're gonna love this integral test because you're gonna solve your homework. Half of your homework you're gonna solve like in seconds, thanks to this integral test. By the integral test, son 1 over x, no, son 1 over n equals 1 to infinity is divergent. Okay? So the next one. The next one is example 2. Decide if the sum of 1 over x squared, oh, sorry, no, x, n squared, n equals 1 to infinity, is convergent or divergent? You need to decide if it's convergent or divergent. Okay, so for that, same thing, right? But probably in practical sense, we need to first decide if the integral is going to work or not. Okay? So let me start with 3. Let's start with condition with the integral. I'm gonna I don't want you to waste time in the exam because if the integral you cannot find, then you cannot do anything. Let's check the integral first. So the function, what would be the function? F of x equals
1 over x squared.
1 over x squared. Okay, so let me give you 4 minutes to find that. Well, 3 minutes to find that integral. Yeah, sorry, x squared. So you need to do 1 to infinity, 1 over x squared dx. That's what you need to do. If it's convergent, then the series is gonna be convergent. If we prove the 3 conditions. Okay, but let's see first if we can do the integral, because sometimes the integrals are too hard. So what even bother to check decreasing or all those? Okay, so let's do it. So I'm gonna do this integral. So as we learned with the limit, a goes to infinity of integral 1 over a and 1 over x squared dx. Then I put this guy here, limit a goes to infinity. Excuse me. 1 to infinity, no, 1 to a x to the minus 2 dx. And then we integrate that. So what is the integrity of x to the minus 2? What is it? X to the
-1.
minus 1 divided by minus 1, right? And then evaluated between 1 and a. So I get, when I put the numbers, I get minus 1 over a plus 1, right? So what is this limit? Limit of minus 1 over a.
Is it 0?
0, correct. So what is the whole limit?
1.
1. So this integral is convergent. So the integral from 1 to infinity of 1 over x squared dx is convergent. So now, if we want to use the integral test, so first f of x, that is 1 over x squared, is continuous on 1 to infinity. Okay, 1 over x squared looks something like that, like this. This is 1 over x squared. But it's continuous from 1 to infinity. So I only care from here, from 1. So the function is continuous after here. Is this continuous at 0? But I don't care because I want it from 1 to infinity. Second, f of x is positive. And f of x 1 over x squared is positive. And that's right? Because it's the square, so that's fine. It's always positive. And the last one is f of x is decreasing. F of x is decreasing. That's also easy because I have f of x is x to the minus 2, right? Therefore, f prime of x equals minus 2x to the minus 3. So that gives me minus 2 over x cubed. And since is decreasing on 1 to infinity. Okay. So why 1? Because sequences start at 1, right? But you see, from minus infinity to 0, the function is increasing. But I don't mind because I don't care about what is happening before. I care about what happened after 1 because a sequence starts at 1. Okay. So I have a department meeting at 3:15. So I'm gonna give you the main statement, and we're gonna prove it next time at the beginning of the class. Okay. Let me give you what is the general term. So this is called a P series. You're gonna love this. So it's gonna save you a lot of time. The P series sum n equals 1 to infinity 1 over n to the P is convergent if P is bigger than 1. And divergent if P is less or equal than 1. Okay, so what does it mean to you? Let me put this here. We're going to prove that next class. So we'll do the same we just did today, but I don't wanna be late to my meeting because it's an important meeting. And I don't want to hurry with the proof. So for example, you guys tell me, example. Sum of 1 over n cubed, n from 1 to infinity. Is this convergent or divergent?
Convergent.
Why? It is because what?
Because the P would be like the exponent, so it would be greater than 1.
So you can say because it is a P series and P equals 3. So P series are convergent for P bigger than 1. Okay. P series are convergent when P is bigger than 1. Okay, so you need to justify, okay? It's not too much to ask because this is a problem. So this is probably 5 points. So, but you need to justify, okay? Otherwise you just put in your calculator and your calculator tell you the answer. So that's no good game. So what about sum 1 n to the 4? What do you guys say? Convergent or divergent?
Convergent.
Convergent, same reason. But you need to write it down, okay? I'm not gonna write it down, but so let me give you another one. Sum of n equals 1 to square root of n. It's convergent or divergent?
Divergent.
Yeah, why?
Why? 1/2 is minor than 1.
Yeah, so it is divergent because it is a P series with P equals 1/2. And you can write it like and sum of 1 over np n equals 1 to infinity is divergent for P less or equal than 1.